Welcome back to McMaster University course Computing and Software 701, Logic and Discrete Mathematics. My name is Bill Farmer, and we're going to start a new topic entitled Propositional Logic. So what is logic? There's different ways that logic could be defined. The most common way of defining it is the study of the principles underlying sound reasoning. Sound reasoning is reasoning that leads to truth. The central ideas of logic are truth and logical consequence, and we'll learn more about precisely what these mean as we go on. Another way of defining logic is it's a particular branch of mathematics, the branch that underlies mathematical reasoning and computing. Now, traditionally, there's three main areas where logic is applied: in computing, in mathematics, and in philosophy. Now, logic deals with some very fundamental distinctions. These are distinctions that are not often made in other disciplines, but in logic, they become very important. So the first one is between syntax and semantics. So syntax deals with how expressions are formed, what they look like, what kind of structure they have. And semantics deals with what expressions mean. So for instance, if I write down the numeral 102, if we think of this syntactically, this is made up of three digits. The first digit is 1, second is 0, third is 2. But if we think about its value, we think it denotes the number 102. And now there are connections between the syntax and the semantics. We know that if the first digit is non-zero and there's three digits, it must denote a number greater than or equal to 100, for instance. Okay, so that's syntax versus semantics. The next fundamental distinction is language versus meta-language. So suppose we have a language, and this language we call L. We can use this language to talk about whatever it's designed to be talked about. Now we could also have another language here, I'll call ML, and this is a meta-language, and this language, its purpose is to be able to talk about the language L. It's a language that's suitable for talking about L. That is the meta-language. Now, in natural language, like English, English is its own meta-language. So in English, we can talk about, for instance, the structure of sentences. We can talk about nouns and verbs. So English is suited as a language that is its own meta-language. Now, formal languages that we use in mathematics and we use in computing, often the meta-language and the language are not the same thing. They're separated. And we want to often make this distinction. And sometimes when we're talking about the language, we call that talking about the language as an object. So this is what's called the object level. And then when we're talking about, so when we're working with the language, we're at the object level. When we're talking about the language, we're at the meta level. The next distinction is between truths and proof. Truth is a correspondence with reality, and proof is an argument that something is true. And these are different. For instance, we can write down or think of a statement in mathematics like there exists an odd perfect number. Just to remind you what perfect numbers are. 6 is a perfect number because it's the sum of its divisors, not including itself. 28 is also perfect. The interesting thing is no one knows if there's an odd number that's perfect. Well, there either is an odd number that's perfect or there isn't. So the truth of that statement will either be that there exists an odd perfect number, will either be true or false. But we don't have a proof. No one has come up with an argument to show that the statement is true or not. We're going to be looking at this distinction a lot more. The next distinction is between a theory and a model. So if we think of a model in the most general sense, it models some aspect of reality. We can have different kinds of models. We can have different models that all try to model the same thing. But a theory is a specification of models. So this is a specification of models. And we're usually going to think of axiomatic theories. We'll define what that is later. So we're going to think of axiomatic theories. And we're going to think of models as being mathematical structures. So in this case, a theory will be a specification of mathematical structures. But it's often convenient to think about a theory as a model itself. So we could talk about a theory of partial orders, and it specifies a bunch of models. Those models are all partial orders. So the partial orders are models of reality where things are ordered in a partial sense, and a theory of partial orders is a model of all partial orders. Anyway, these distinctions will become clearer as the course goes on. So the next question we want to ask is, what is a logic? Informally, a logic is a system of reasoning. It's a system for performing reasoning. But formally, a logic is a family of formal languages that have a common syntax, a common semantics, and they have concepts of truth and logical consequence. So this is what a logic is. And logics may also have proof systems for mechanically deriving that a given formula is a logical consequence of a given set of formulas. So in my definition of a logic, proof systems are optional. Sometimes people define the logics where you have a common syntax, a common semantics, and a proof system. Right? Let me say that more accurately. You have a common family of languages, a common syntax, and a proof system, and then it's optional what your semantics is. But the way I've defined it, the proof systems part is optional. Now, there's different kinds of logics. From computing and mathematics, the most important examples are propositional logic, which we're going to look at in this topic, first-order logic, which we'll look at later, set theory, which is very important for mathematics, but we're not going to pay a particular attention to it. And then there's two flavors of type theory, simple type theory and dependent type theory. Simple type theory is classical higher-order logic, roughly speaking, and dependent type theory is constructive higher-order logic. We'll talk later about the difference between classical and constructive. It's probably worth saying that most of the interest in classical higher-order logic is in computing, and same way with constructive higher-order logic. So these are much more, there's much more interest here in computing, and here there's more interest in mathematics. By the mathematics community, I should say. So we're going to look at propositional logic. What is propositional logic? It's the study of the truth or falsehood of propositional formulas. So these are also called propositions, and these formulas are formed with propositional connectives. So a simple example would be A where we use this symbol to represent A and B. Now, in propositional logic, A and B are both going to be propositions. A could be, my dog runs faster than any other dog in the neighborhood. And B could be, a double eagle is worth $20. In propositional logic, we don't care what the propositions are. We only care how propositions are put together using connectives and what truth values get assigned to them based on these connectives. So propositional logic is reasoning about proposition in such an abstract way that we don't really even care about what the propositions are. Now, this is also called sentential logic, and surprisingly, the work on propositional logic began with the Stoic philosophers in ancient Greece, but particularly one named Chrysippus, who worked in the late 3rd century BCE. He is one of the really key developers of the ideas of propositional logic. Now, most logics that you'll run into are extensions of propositional logic. So in one way or another, propositional logic sits inside those logics. Now, there's many applications of propositional logic. It's, like I said, part of basic logical reasoning in most common logics. It is the basis for designing logical circuits in electrical and computer engineering. And many problems can be encoded as satisfiability or tautology problems. These are basically special kinds of problems of propositional logic, which we'll talk about later. Now, we're going to develop propositional logic more or less following the chapters of 2 and 3 of Ben Ari's book, Mathematical Logic for Computer Science. Okay, so let me back up a bit. Remember what I said a logic is. I'm going to use a different color here. A logic is a family of languages with a common syntax and a common semantics. Okay, so I'm going to define propositional logic as this family. And we're going to look at syntax, then at semantics. So my family is going to be defined by picking an countably infinite set of symbols called atomic propositions. So these are just symbols. They represent propositions. They represent statements. And as I said, we're not concerned about what the statements are. So two different propositions will represent two different atomic propositions will represent two different propositions. So we're going to call these atomic propositions, but they're also called atoms, propositional symbols, propositional variables, or propositional letters. They behave in some ways like variables. So we have this set of symbols, and in addition we have a bunch of Boolean operators, and we're going to have a rather full set of these. We're going to have not, or, and, implies, if and only if, and if and only if stands for if, and only if, but it's very often written as IFF, exclusive or, NAND, which stands for not and, which is also called the Sheffer stroke, and NOR, which stands for not or. It's also called the Pierce arrow, so we have these two. And then notice that all of these are binary operators except for not, which is unary. Binary means it's going to take two propositions as arguments. And these Boolean operators are also called propositional connectives. Now, we can define a set of propositional formulas. This is what we really want to understand and study. These are going to be strings that are inductively defined by two rules. The first rule is every atomic proposition is a propositional formula. That's what this says. And the second says if A and B are propositional formulas, then all the different things we can get by applying our Boolean operators, they are all propositional formulas. Now, from now on, when there's no loss of meaning, matching pairs of parentheses, let me show you what these matching pairs of parentheses, we will drop these when there's no loss of meaning. Okay, so that's the syntax. It's pretty simple. We have this basically inductive set of propositional formulas, and we get these formulas in two ways. The atomic propositions are formulas, and we can build up more complex formulas using our Boolean operators. Okay, so now we're going to look at the semantics. So we have our language. Our language depends on what what atomic propositions we have, and we are assuming we have a countably infinite set of them. Okay, so we're ready to define the semantics. The first thing to notice is that we're going to have a standard kind of semantics. That means we're going to think of our formulas as always denoting either the true value or the false value. So this set is going to be the set of the standard truth values. So there's just two values, true and false. And then an interpretation is a total function, script I, which maps each propositional letter to either true or false. That's what interpretation is. Where in other words, we have these atomic propositions. We can also just call these atoms. We have these atoms. They represent propositions. And an interpretation will be saying which ones are true and which ones are false. Now, interpretations are also called truth assignments for obvious reasons. Okay, so now let's say we have a formula and we have an interpretation. And we're going to define the truth value of A under this interpretation, which we write like this. D sub I of A. So this is going to be the value of A under I. And this is defined recursively on the structure of A. And it's defined in the next slide. Here it is. It's a long definition because we have a lot of different Boolean operators or logical or propositional connectives. But basically, we have a bunch of rules. The first rule says that if A is an atom, then the value of A under this interpretation will be whatever the interpretation gives A as a value. So that's going to be true or false. The next one says the value of not A will be true if the value of A is false. That's what we would expect. The value of not A will be false if the value of A equals true. And we can go on. Let's do one more. Or the value of A or B will be false if the value of A is false and the value of B is false. Otherwise, the value of A or B is true. So this defines all the rules for all the connectives, and using these rules, if we have an interpretation, we can determine the value of any propositional formula. Okay, so one thing that's useful is a truth table is a way of displaying the semantics of a propositional formula. So let's just take a simple example. So let's say I have this propositional formula. Not P or P and Q. So P and Q are atoms. And I left out parentheses, but I could put those here. So I'm going to show you how we can explain the semantics of this formula using a truth table. So the truth table starts off, we have whatever atoms we have 2 here, and then we put down all the possible ways we can assign truth values to these. There's only 4 ways because we have just 2. And now what I'm going to do is I'm going to work out step by step what is not A, not P. Well, here's what P is, and so it's going to be really the opposite, the dual of whatever value we have. So here P is false, it's going to be true. So the next thing I'm going to do is put P and Q. And we know P and Q, because this is conjunction, this is and, this will only be true if both P and Q are true. Both P and Q are true only in this case. So here we're going to have false. And then finally, the thing we're really interested in is this. And this is an OR. And we know that this will only be false if both not P and this is false. And the only place they're both false is here. So not P is false in this case, and P and Q is false in this case. In all the other cases, it's going to be true. That completes our truth table. Okay, so the next thing I want to look at is the notion of logically equivalent. So we'll say that 2 propositional formulas, A and B, are logically equivalent if the value we assign to A equals the value we assign to B for all interpretations. So we always have the same, these 2 formulas always get the same values for every interpretation. That's what it means to be logically equivalent. And we could test this out with a truth table. So let me go back here. If you look at, here we have 3 situations here. Now there are there's an infinite number of interpretations, but all the interpretations fall into 3 classes. And the 3 classes are P gets false and Q gets false, that's 1. P gets false and Q gets true is 2. P gets true and Q is false, and both of them get true. So there's 4 classes. Now there's a countably infinite number of of atomic propositions or atoms. We don't really care what values we assign to those. It doesn't matter because they don't occur in the formula we're interested in. So for that reason, our infinite number of interpretations squish down into just 4 different types. And those 4 different types depend on how truth values are assigned to P and Q, because P and Q are the only atomic propositions that occur in our formula. Okay, so let's move on. So let's just say we have a formula A. We'll say A is satisfiable if there is an interpretation that makes A true. If there's some interpretation that makes A true, it's satisfiable. Sometimes people like to think of interpretations as being in different worlds. You can interpret this as saying there is a world in which A is true. And we call this interpretation a model for A. So A is satisfiable if it has a model. So that's a very important notion, satisfiable. Another important notion is valid. And we write valid like this, with this double turnstile symbol. So valid means that A is given the value true for all interpretations. So if we think about it in possible worlds, A is valid in every possible world, in every interpretation. And often in propositional logic, we call propositional formulas that are valid, we call them tautologies. They're statements that are going to be true in every possible world. So one of the classic tautologies is this: A, not A or A. Not A or A in classical reasoning is true in every possible situation. Now we'll say A is unsatisfiable if it's not satisfiable, and we will say it's falsifiable or invalid if it's not valid. So we have these four different possibilities. And then there's a useful little lemma that says A is valid if and only if A is not satisfiable. So let's go back to our example. And we have this formula right here. Is this formula satisfiable? Now, satisfiable means it's given the truth value true for at least one interpretation. Yes, it's actually given in 3 different cases here. So yes, this is satisfiable. Is it unsatisfiable? Unsatisfiable means it's not satisfiable, which would mean that we'd have falses all the way down. No, it's not unsatisfiable. So I'm going to say not unsatisfiable. Is it valid? Well, if it were valid, we'd have to have trues all the way down. We should be assigning the truth value true in every interpretation. So it's not valid. Is this falsifiable? Falsifiable means it's not valid, which means it's not true everywhere. Yes, it's false here. So it is falsifiable. It's satisfiable, falsifiable, it's not unsatisfiable, and it's not valid. Now, remember we said, let's go back and look at our lemma. A is valid if and only if not A is unsatisfiable. So it will help. Let me just write that down. A is valid if and only if not A is unsatisfiable. So why is this true? Well, A is valid would mean that we'd have trues at every place in the last line. A, not A, is unsatisfiable would mean that, well, what does unsatisfiable means? It means we would have false everywhere. So if we had true everywhere, then not A, we would have false everywhere. And so then not A would be unsatisfiable, and it works the other way. So if you just look at the truth table, it is obvious why this is true. It follows right from the definitions. And the reason I called it a lemma is because this is a very useful fact for proving things in propositional logic. Okay. One more slide about semantics. This time, let's say we have here a set of propositional formulas. We can say that set is satisfiable. If there's some interpretation that makes every formula, assigns to every formula in the set true. So we're thinking of the whole set as being satisfied. And we say that the interpretation that does this is a model for you. Okay, now the next definition is very important. So I'm going to clean up everything before we get. In fact, I'm going to circle it. This is really important. That's what I'm looking at. So we say A is a semantic consequence of U. So A is just a formula. U is just a set of formulas. And we write it like this. This means A is a semantic consequence of U. If every model of U is a model of A. What is a model of U? It's an interpretation that makes everything in U true. So if we have a model of U that makes everything in U true, and then if that model is always makes A true, we will say A is a semantic consequence of U. Another way of thinking about that, if we have a world in which everything is in U is true, and then an A is a semantic consequence, then it must also be true in every model that makes everything in U true. So this is a very important idea, the notion of a semantic consequence. And remember we had this notation which said that A is valid. Well, we can write this instead of this, because this notation says A is a semantic consequence of the empty set of formulas. So A is a semantic consequence of the empty set of formulas is the same thing as saying A is valid. Now, semantic consequence is a special case of logical consequence. And we will see other examples of logical consequence later. So this completes the story for today. And we will continue with complete sets of propositional connectives in our next lecture. Goodbye. See you later.